Hey everyone, thank you, Geordie. Thank you for organizing this and for having me. Um, is there any way that you could turn me around so I can see people? I feel a bit like I'm speaking into the void. Hey everyone. Um, cool. So yeah, I'm going to be talking about why it is hard to estimate synthesizer parameters and why perhaps it doesn't need to be. Um, So yeah, as Geordie mentioned, the context here is sound matching. This is sort of broadly the task of we have some audio. We want to find parameters for a synthesizer that allow us to approximate this audio. Um, it's a fuzzily defined task. It's not clear what a good match is. The sort of convention that's emerged in the literature is that we're minimizing some kind of audio distance, but this is still a cloudy definition. And so we're going to cheat a little bit for the rest of this talk and focus on synthesizer inversion. So we're just going to assume the sound that we're matching came from the synthesizer. We do this without loss of generality, at least in terms of the issues we're discussing, because as it turns out, this is kind of a necessary step in sound matching anyway. And so if there is a problem that affects inversion, it also affects sound matching. And so historically with these kinds of methods, there's been something of a compute quality trade-off. There's a lot of really cool work that uses these very exploratory optimization algorithms, particle swarms, genetic algorithms, etc. These can get very good results, but we're effectively kind of trading CPU cycles for quality in a way that doesn't gel nicely with music production workflows. Um, and so I guess the hope with machine learning, with neural networks in particular, was that we could sort of amortize the cost of this. So we train once, and then hopefully we can just sort of quickly infer things as many times as we want. And in practice, this didn't quite materialize in the way we wanted because the quality of the outputs of these neural network-based systems was not consistently high. Something that worked in one case did not work well for other synthesizers, and so on. Um, and so in this talk, I want to ask why we can train neural networks that appear to think. We'll avoid the philosophical rabbit hole of whether they actually do, but they can do pretty amazing things. And yet we can't take a sound that we know was produced by a particular synthesizer and easily find the parameters that recreate that sound. That seems insane. So why can't we do that? Um, and the answer I'm going to argue is that, well, we can. We've just been training them wrong. Um, and some of the ways in which we've been training them wrong include just using naive regression. This is kind of what most work relies on. And this completely collapses in the face of any uncertainty, as we will discuss later in this talk. We've been using DDSP, which is a very exciting development. It seems like we could specify our optimization task in terms of arbitrary audio distances. In practice, it's very fiddly. We're limited to things we can implement differentiably or where we can estimate the gradient. And actually, there's all sorts of crazy optimization challenges that make this very difficult. And the same kinds of issues affect proxy style models, which have been slightly less popular, but there have been a couple of works. And these are also quite hard to train due to some instability. So what all these have in common is that what we get at the other end of the training algorithm is a deterministic regression model. So for a single audio signal, we produce a single point estimate of the parameters that produced it. You'll notice I've got y and x backwards here, and this is because we're learning the inverse, right? Y is our audio, x is our parameters. The forward process is y is g of x, let's say, where g is our synthesizer. So why is this a problem? Well, most synthesizers can produce the same signal given multiple different sets of parameters. And this is a really important point, so I'm going to repeat it. So you can get the same signal from multiple different sets of parameters for most kind of production-ready commercial audio synthesizers. And if we relax our definition of same slightly to include very similar or maybe equivalent under some, say, phase invariant audio representation, then this is even more the case. Why does this matter? Let's look at a really simple toy example. So forget synthesizers. Let's just say our forward process is we are squaring a number. So we're saying y equals x squared. And now we're trying to invert this with a neural network. So we sample a bunch of data points, these blue points here, right? So X-axis is our Y value and our Y-axis as our X value. I know that's a bit confusing, but that's because we're going backwards. Right, so we sample these blue points and we train our neural network, and we learn something that looks like this orange function, because the network doesn't know anything about the intrinsic symmetry of this task. And so normally in deep learning, we have two sort of big levers we can pull. We can try and scale up the model. If we do that here, well, what happens? We just get a much more detailed orange function, which is still completely pathological. It's still just interpolating these data points. And the other thing is we can scale up our data set. We can collect more data. If we do that here, all we're doing is creating more and more oscillations between these two possible solution modes. So clearly, just approaching this with naive regression is broken. And I want you to keep this image in mind, because this is really what underpins everything that I'm about to talk about. So how does this show up in synthesizers? There's a few ways. First, there's what we might call trivial indeterminacy. So this is where we have parameters that are inactive. So we can change them and the signal will be the same. So a super trivial example is if we turn the global volume control down, then none of the other parameters do anything, right? This sounds silly, but actually it creates a mapping that can't be represented by a continuous neural network trained for regression. Sadly, we don't have time to go into details about why, but I guess trust me or read our paper. There is also non-trivial indeterminacy. So this is when we have active parameters, so parameters that do affect the signal, where multiple configurations of those parameters produce equivalent signals. So we might have an oscillator and a resonant digital filter, both being capable of producing a sine wave that can be modulated by other parts of the synthesizer. And this is a problem because when we train by maximum likelihood estimation, we converge on an expectation over these equivalent solutions. So instead of getting one or the other, we get an average over them, which is clearly wrong. And then a special case of this non-trivial indeterminacy arises due to what we might call structural symmetry in the synthesizer. So for example, we might have multiple oscillators that do the same thing. So if we swap their parameters around, we're going to get identical signals. So our parameter representation is different, but our signal is the same. And we again face this issue with converging on the expectation. And this permutation issue also creates discontinuities in the output space. Okay, so what do we do about this? Effectively, we have to abandon the regression approach. And instead, we should explicitly model our uncertainty, the fact that we don't know which of these sets of parameters produce the signal. And so we're going to do this by learning a probability distribution over parameters conditional on our audio. Now, we don't need to actually explicitly formulate this probability distribution. We can instead just learn to sample from it. And this is just training a generative model. So we're now going to approach sound matching or synth inversion generatively. So this begs the question, how do we do this in the space of synthesizer parameters? And how do we ensure it actually responds to our audio conditioning? Because this is a very rich, high-dimensional conditioning signal. So there's been some prior work. If you've been in the field for any amount of time, you probably are familiar with flow synth from ACIDS at IRCAM. This was a really awesome pioneering piece of work. And the way it worked was training a variational autoencoder in audio space, and then learned an invertible mapping from the latent space of that VAE to the parameter space of the synthesizer. Now, this was a really cool idea, but actually, sadly, the way they were forced to train this bridge between audio latent space and parameter space also suffered from the expectation problem. So this was a step in the right direction, but it didn't solve these underlying issues. And so what we propose to do instead is to use continuous normalizing flows. This is a modern family of generative model, which we can train using a technique called flow matching. By pairing this with a technique called classifier-free guidance, we're able to enforce audio conditioning in such a way that we can just directly train our model in parameter space. And as an added bonus, there's a neat result in the literature that means we can get a symmetry invariant model or a symmetry invariant probability distribution by using a symmetry equivariant model. And so to deal with permutation symmetries that pop up in synthesizers, like between oscillators, here we can just use a transformer without a positional encoding. So there's one more consideration, which is that real synthesizers are very complex. We may not know exactly how these symmetries manifest in the parameter space. And they also exhibit these sort of symmetry-like structures, which are incomplete. Again, sadly, we don't have time to go into much detail on these, but check out our paper or ask questions about them. But effectively, we introduce a module. It's a sort of input module for this kind of equivariant transformer that allows us to adaptively discover symmetries if they're present, but we're not constrained by them if they're not. Okay, so I've got a couple minutes left. So in that time, let's do some actual science. So we did some experiments on all this. So the first is just a simple toy task. So we design a very simple synthesizer that consists of K oscillators, each with 3 parameters, and we just sum them together. And so this is permutation symmetric. We can swap the parameters of these oscillators around without changing the sound. But we can create an asymmetric version of this by limiting the frequency range of each oscillator to a separate interval along the frequency axis. And so in doing this, we can test the effect of permutation symmetry on our models. So we train a few feed-forward models. Firstly, just a simple regression model. And secondly, 2 variants that try to account for the permutation symmetry in ways that we've seen in the literature. Then we also train a generative model without any sort of inductive bias to symmetry, as well as a generative model with a strict inductive bias to symmetry, and finally one with our parameter token input module. And these are our results. Given the ticking clock, I'm going to say let's just focus on these left 2 plots, which look at audio distance. And so very interestingly, we see that the blue squares, the just feed-forward regression model, struggles, forms even worse than random under symmetric conditions. But when we break the symmetry, it's one of the best performing models. And we see the inverse of this for our equivariant generative model. So performs incredibly well under symmetric conditions, but when we break the symmetry, it performs very poorly because it's now imposing an inappropriate constraint on the outputs. What's really nice is our parameter token model, this green square, it basically lets us enjoy the best of both worlds. When there's a symmetry present, it's able to make use of its inductive bias, but when the symmetry is not there, it simply learns to break this and behaves like a regular model. Okay, so this tells us that symmetry has an effect, and it shows us that our intuition is correct. We can use these generative models with a symmetric bias to overcome it. What can we do with this? So we train on SurgeXT. This is a big, full-featured synthesizer with hundreds of parameters, audio effects, multiple modulation sources, and loads of symmetries, obvious and less obvious. We don't have time to really dive into result tables, I don't think. So let's just jump to audio. But basically, it works. So here is some ground truth audio sampled directly from the synth. Can you just give me a thumbs up if that came through? Great. And here's what our model is able to do. And here's what the previous best performing state-of-the-art benchmark could do. Another bunch. So you can hear that it's able to get much, much closer, even on these very fiddly parameters like LFO rates and things like this. And while we didn't do anything to make this adapt to out-of-domain audio, and this wasn't our focus, remember we're focusing on inversion, not matching, we do have some out-of-domain results too. Maybe I'll just play one of these for time. So you can see the kind of benchmark model just completely breaks down with this very out-of-domain signal, whereas our model appears to have generalized to some extent. Okay, very quick wrap up. So neural networks did not appear to be able to do sound matching or synth inversion. We're arguing this is due to unaddressed indeterminacy and symmetry. So the takeaways here, if there's indeterminacy, use a generative model. If there's symmetry, use an invariant generative model. And if there's something you don't know about the symmetry, use a generative model which adaptively discovers symmetry, like ours. You can find code and more audio examples in our paper at this QR codes, which I'll leave on the screen while I take any questions. Thank you.